working? Okay. Yeah, this projector is broken. The one over here. So just that's what's going on. Okay. Today we will look at the Nelder-Mead method for optimization, and this is just another algorithm for optimizing a function, which is basically finding where the minimum of a function exists. This is for multi-dimensional functions, and we've looked at one other multi-dimensional optimization method, which is coordinate descent. In 102b, I cover gradient descent, but that's not everybody does gradient descent in 102b, but I cover that. But anyway, we'll look at the Nelder-Mead method. And the Nelder-Mead method is a direct search method, meaning what you do is it feels kind of like you're not brute forcing it, but you evaluate the function at one location, you evaluate the function at another location, and you compare values, and you go, oh, this one's lower, we're moving in the right direction, kind of thing. There's no derivatives. It works pretty well, but it's not guaranteed to converge. It's kind of just a system for searching for better values. And the way it works is it uses a simplex. Basically, for a two-dimensional function, well, for any dimensional function, a simplex is going to be a shape with n plus 1 vertices. So if you have a two-dimensional function, your function is defined over this two-dimensional plane. Your simplex is a triangle, basically the smallest kind of shape you can, or the simplest shape you can have that has like an internal area, right? A triangle. So you're going to have a shape with three vertices. If you have a three-dimensional function, your simplex will be a tetrahedron, this pyramid, kind of this pyramid thing. And then in four-dimensional space, which we can't directly visualize, you have a 5-cell, I guess this is called a pentachoron, and so on and so forth. There is a picture of a pentachoron. This is a three-dimensional projection. This is a shadow, a three-dimensional shadow of a four-dimensional object, and this is what it looks like when you rotate the four-dimensional object. The three-dimensional shadow looks like this, which I don't know. It's all a little bit trippy, right? Thinking about four-dimensional space. But anyway, to illustrate, we'll just look at the two-dimensional, and we'll have a triangle, and we'll use the triangle. And basically, you start with this simplex, and in our case, we have a simplex, a triangle in two-dimensional space, and we're going to use this to find a minimum. Okay. So you just start off with arbitrarily selected points. In our case, we're going to have 3 arbitrarily selected points to form a triangle. And we're going to do these steps: sort, reflect, extend, contract, shrink, and we'll check convergence. So we're going to do, basically, we'll sort them, and then we'll do one of reflect, extend, contract, or shrink, depending on what values we find, and then we'll check convergence. And that's going to be each iteration. At each iteration, we'll sort them and check convergence, and in between checking convergence and sorting and checking convergence, we'll do one of these steps. Okay, but we always start off with reflecting. Okay, so anyway, let's talk about sorting them. So let's say these are my 3 arbitrary points, U, V, and W. Okay, so I have this triangle, and I evaluate the function at all 3 vertices of my simplex, and we sort them so that U has whichever point has the best value, meaning you evaluate the function at that point, and it's the smallest value of the three, that's going to be labeled u. And of the 3 points, the one that has the worst performance is going to be called w, and v is somewhere in between. Okay, so u is the best, w is the worst, v is somewhere in between. Right? And it doesn't matter whatever, we just call this u, v, and w. And so w is the worst performing point, and we're going to try to improve our triangle by getting rid of w and replacing w with a better performing point. Okay? And so the first thing we're going to do is we'll do a reflection. We're going to take w and reflect it through the midpoint of the other two vertices. So we find the midpoint of u and v, which will be right here, and then we're going to reflect w through that midpoint. So, and that takes me to r. So if you think of, if I called this m, you can think of a vector wm, and r is going to be m plus wm, if you can visualize that. So if you imagine a vector going from w to the midpoint, then r is going to be the midpoint plus that vector wm. That will take me to the reflected point. Okay, but we reflect w through that midpoint to get r. Okay, and we evaluate the function at this reflected point. And if the function is better, if at the reflected point the function is better than v, okay, so that we have r is now the second best point, we'll just take it. Okay, we'll take it, and this will become our new triangle. So if u is still the best point, r is the second best, and v is the worst point, this will become the triangle at the next iteration. Okay, but what do we do if we reflect it and r is even better than u? We do something else. And what do we do if we reflect it and r is not better than u or v? Okay, we're going to do something else. Okay, so if we reflect it and r is somewhere between u and v in performance, we will just take this new triangle. If r is even better than u, so r is now my best performing point, we're going to just attempt to be a tiny bit greedy. We're going to say, you know what, moving from w to r, moving in that direction, got us really good performance. It got us even better than my current best performing point. R is even better than u. So let's just try being a tiny bit greedy and keep moving in this direction. And so we're going to extend it even further. Okay? So what you can think of is, again, think of the midpoint right here. You take this vector from w to the midpoint. You add that vector w to the midpoint to get to r. You add that same vector wm to r, and you'll get to e, right? So if you take the midpoint plus 2wm, that will take you to e. Is that okay, as far as where e might be located? And we're going to evaluate the function at the extended point. And if the function at the extended point is even better than r, so now you get an even lower value, we'll take e, and my new triangle will be UVE. If e doesn't outperform r, then we'll take UVR. Okay, so we're going to extend if r, if the r is better than u, we'll try extending it. If e is even better, we'll take that. If it's not, we'll take r. All right, and so the other possibility is we reflect w through the midpoint. We're at r, and let's say r is not even better than v. Okay, so you do you start off with UVW. W is your worst point. You reflect it. Even if r is better than w, if r is not better than v, then r is still your worst performing point. And if r is your worst performing point, you don't want to take it, because if you accepted UVR and r is your worst performing point, then and you start the process again, you're just going to reflect it back to w. Okay, and that's not going to be any better, right? You're just replacing the worst point with a less worst point, but it's still your worst point, and then you'd flip back, and you'd kind of just be flipping between w and r. So if you reflect it and R, even if R is better or worse than W, if it's not better than U or V, then we're going to have to try something else. We're going to try contracting it. Okay? We have the inside contracted point and the outside contracted point. We're going to try these two contracted locations. The inside contracted point we'll say is 1/4 of the way from W to R, or half of the way from W to the midpoint. The outside contracted point is 3/4 of the way from W to R, or maybe halfway from the midpoint to R. Okay. And technically 1/4 and 3/4 aren't like fixed values. Those are probably the most common values we use, but it's not, you're not breaking any laws by saying, I want to go 1/3 of the way from W to R and 2/3 of the way from W to R, or 20% of the way, or 80%. You could pick whatever values you want. Probably, 1/4 and 3/4 are most commonly chosen, but you can, if you wanted to, you could tweak your decisions and pick a slightly different location as well. But we're going to try out these inside contracted points. We're going to evaluate both of these. And hopefully one of them is better than V, okay? And in that case, we'll take whichever one does better. Okay, so we'll evaluate both of them. Whichever one does better than V, and which one does better than the other, we'll take that one. Okay, and the final option, and this generally only happens as you get really close to the final solution, is if you reflect the point and it's still your worst point, and then your two inside contracted points are still worse than V. Okay, so you check the reflection, you check the inside and outside contracted points, and they're all worse than your second best point. Then in that case, you just shrink the triangle towards U, because right now U is our best performing point, and so we're just going to say, let's try moving closer to U. And so you're going to replace V with V prime, which will be halfway from U to V, and you'll replace W with W prime, which is halfway from U to W. And so you're just shrinking towards your best performing point U, and then you'll start the process again. You have a new simplex UVW, you'll reflect it, maybe you'll try extending it, maybe you'll try contracting it, maybe you'll shrink it, okay? And then finally, you'll check convergence. You check convergence to see if you should stop. One method is to look at the corners of your simplex, and you take the standard deviation of the function at the simplex. If all three corners have very similar values, meaning your standard deviation is very, very small, below some tolerance level, maybe your program will quit. Okay. You can also just kind of see if the difference between the max x and the min x of your three corners and your max y and min y of your three corners is also, if the difference between all of these things is smaller than some tolerance, you can also quit. It gets more complicated as your dimensions increase. You have to check a whole bunch of min max values for every dimension, but that's another way. But because you're kind of evaluating the function at every single corner, these values are available, and you can just kind of check the standard deviation there. Okay, so once again, we'll sort them, and you'll do one of the following: reflect, extend, contract, or shrink. You always do the reflection, but whether you accept that reflection or not depends on everything, right? So you have UVW, you're going to reflect W through the worst point. If it's better than V but not better than U, you take the reflection. If the reflection is better than U, you'll try being greedy and you'll try an extension, and you'll take whichever one is better. But if reflecting is not better than V, then you try contracting and you take whichever one is better. And if all of these things fail, then we'll shrink it. All right, let me just go ahead and give you all three view quiz answers. All right, and it's real simple. the answers are A, B, C. Okay? A, B, C for your 3 view quiz answers for today. And then, okay, so now I have this video demo of the Nelder-Mead algorithm. All right, so these are contour lines of my imaginary 2-dimensional function. The function is this, x1 squared minus x2 squared, or x minus y quantity squared, plus x1 minus 2 quantity squared, plus x2 minus 3 quantity to the 4th power over 10. And so it's this kind of this awkward bowl-shaped thing. And the minimum is located somewhere around here. And you can kind of see I have these contour lines printed so you can kind of see it. And just arbitrarily, I decided to start in this corner, 0, 0, 1, 0, 0, 1. And so we're going to evaluate the function at these 3 points. Okay. So again, I guess in real life, you would not know that the function has these contours, right? You just you're given a function, and you're going to evaluate the function at these 3 points. Okay. And so we say, okay, which one we're going to sort these points, okay? And so we start off, and as far as these 3 points go, this corner 0, 0 is the worst. It's just ever so slightly worse than this one. So if you look at the contour lines, you can see this one is just a tiny bit closer to the contour line, and this one's a tiny bit farther away, indicating that it's just a little bit higher, as far as, I don't know, altitude goes or something, okay? And this one's our best point. This one's our best point, okay? So I reflect the worst point through the midpoint, and I end up over here. And we evaluate this point, and we say, is this better than my best point? Or is it better than my second best point? It is. Is it better than my best point? It is also better than my best point. So because this is now my new best point, I'm going to just say, let's try being a tiny bit greedy, and let's extend it even further. So I extend it even further, and I say, is that even better? And it is. We're moving in the right direction towards getting towards the minimum. So we will take the extended point, and this is my new simplex. So this is going to become my new simplex. So I evaluate this. What's my worst point? This is now my worst point over here. Okay, I'm going to reflect this. Okay, I reflect it through the midpoint, and I end up over here. And I look at this point, and I say, is this better than my second best point? Okay, this is my second best point. It's better than that. Is it better than my best point? It's not. So we're going to just take the reflection and accept it, okay? Because if it were better than my best point, then I would try being greedy and I would extend it. But I'm not better than my best point, so I'll just take the reflection and I'll accept that. Okay, so now here's my simplex. Okay, so this is now my worst point, and I'm going to reflect it through the midpoint of the other 2 points. Okay, and so here it is, and I say, is this better than my second best point? It is. Is it better than my best point? It is also better than my best point. So we're going to try being a tiny bit greedy, and we'll extend it, and we'll say, is that better? And we got, it's like we got too greedy, so this is worse. So we won't take the extension, we'll take the reflection. Okay, so this is my new simplex. This is now my worst point. I'm going to try reflecting it. Okay, and we look at the reflection and we say, is that better than my second best point? Here's my second best point. It is better than my second best point, so we will accept it. We're not going to try being greedy. And we could see if I try to be greedy, it would take me to the wrong way, so we're not going to bother. So we'll take this, better than my second best point. This is my new simplex. This is now my worst point over here. We'll try reflecting that. Okay, so I try reflecting this, and we say, is this better than my second best point? My second best point's over here. And we're not quite sure. So let's see what the computer says. It says it is better than my second best point, so we'll take it, okay? So now this is going to be my worst point. This is my worst point. I try reflecting it. Is that better than my second best point? It is not. It's worse than any of the other points. So we're not going to take that. Okay, so if it's worse, we're not better than the best point or the second best point, we're going to try contracting it. Okay, so we will try an outside contracted point and an inside contracted point. So those are my two contracted points, halfway from here to the midpoint, halfway from the midpoint to there. We evaluate both of them and we say which one's better. Okay, this is the better of the contracted points, and the contracted point is better than my second best point, so we'll take it. So here's my new simplex. This is now my worst point. We reflect it, okay? And this is not better. It's better than my worst point, but it's not better than my second best point. So we're going to try contracting again. Okay, so we try contracting. Which one is better? This one's better, so we'll take that one. Okay, we reflect, and we again, this one's not better, so we try two contracted points. And as far as the two contracted points, this is the better one. So here's my new simplex. Okay, this is now my worst point. I try reflecting it, that's even worse. Now I try my inside and outside contracted points. We're going to take the inside contracted point, and so we can see my triangle, shrinking with all of these contractions here. All right, and we evaluate this. This is the worst point. We reflect it, that gets even worse. So we're going to try our contracted points. The green one's the best contracted point. We'll take that. Which one's the worst? That one is. We reflect it. And reflecting it got even better than everything, so we try extending it, and that was not better. So we'll just take the reflection. Okay? And then that's the worst. We try reflecting it. That gets worse. We'll try contracting points, and we shrink, and we reflect, and we evaluate these things. And this is that. And I think I ran out of iterations here. Okay? So just to kind of start from the beginning, we start off here, and we reflect and extend. Reflect, accept that. We reflect, extend. We take the reflection. We reflect, accept it. We reflect, accept. Reflect, contract. We reflect and then contract. We reflect and contract. So as we get closer, we do a lot of kind of contracting our simplex, and we can see the simplex, shrinking and kind of zeroing in on where a minimum location might be found. Okay, that's the end there. You had a question, yes?
For the first iteration, what's the reason that we just don't keep connecting? We go on.
Yeah. I mean, we could, but I guess to kind of keep the algorithm simple, we just try one extension. Now you could probably modify it and just say, hey, if the extension's even better, keep going. But just to kind of keep the algorithm, we'll try a reflection, and if it's the best one, we'll try the extension, and we just, it's like pushing your luck, right? We just say, you know what, let's just try pushing our luck a little bit and try the extension, and you could say, you know what, I want to keep doing it, and you could kind of have, you can make your algorithm more complicated, and maybe you'll get even better performance, but it only really works if it aligns, where everything kind of aligns and you're kind of going in the exact direction that you need to be going, which, it happens. That kind of that would have probably happened in this case, but not necessarily, right?
Would doing that still align with the method?
It would be a modification of it, and certainly, and that's pretty much all of science and research, is just take something that works and you say, hey, can I try tweaking a little bit of a thing and doing that right? One of the parameters that you could tweak is how far should your extension be? Right now, this extension is basically double. Like if you look at the midpoint here and you go midpoint to the reflection, it's basically just an extra version of that. And you could say, you know what, instead of going out 1, you go out 1.5 or 2 or something like that. And that's a parameter you could try tweaking and playing around with. You know, you could keep saying, hey, keep trying the extensions and keep pushing it until you run out. And you know, who knows where it'll take you. But yeah, that's kind of this is how the algorithm's set up. So. Yeah, so that's the Nelder-Mead algorithm. R has a built-in optimization function, and I didn't write any notes to kind of talk about how it's used, but it has different optimization methods that you can choose from, and the default method is actually the Nelder-Mead method because it generalizes to any high-dimensional function. It just has this high-dimensional simplex, right? So, you know, in 3 dimensions, your simplex is this kind of this tetrahedron thing, and you would take if how do I do this, right? Let's say this is my worst performing point up here. You would reflect it through the centroid of the remaining points, right? So you have this, I don't know, some surface here. You're going to find the centroid here, and you're going to reflect the worst point through it, and it works. It works in high dimensions as well. Again, it's not guaranteed to converge. There's you know, probably a whole bunch of other animations. Let's see. All right, so somebody, okay, I don't want to. It's always risky clicking a video on YouTube in class. So, you know, you can search for some Nelder-Mead things and see other animations, but you know, this looks like somebody drew a bunch of triangles as well. I don't know if anybody has animated something in high dimensional space, but you know, we could kind of imagine it there. Okay, but that's all I have planned for today. So we'll just let lecture end here, and I'll see you on Friday, and we'll get into kind of a new topic, randomization tests and things like that. So, or actually, we'll review statistical inference first, but we'll see you all on Friday. Have a good rest of your day.